Welcome to this video on mutually exclusive events. So as you're studying probability, at some point I hope that you're going to run into this mutually exclusive, so kind of this terminology. Now, it relates back to when you have two events and there is no intersection between them, so that means they cannot happen simultaneously. Now, it is a little bit tricky because when you are studying independent events, sometimes you might confuse having independent events with something that is mutually exclusive. Now, for independent events, maybe I'll put up a link up above there, okay, if you haven't watched that video. But coming back to these mutually exclusive events, I'll try to give you, some smaller little examples to tell you about this, mutually exclusive and then what might not be mutually exclusive. So if you take the probability of two events, so let's say events A and B, and let's say you want to know what the probability of either A or B happening is. Now, it is understood as you kind of watch the videos that the probability is equal to just the probability of A happening on its own plus the probability of B happening on its own minus when they can happen at the same time. So mutually exclusive or kind of events that cannot happen at the same time, so they're sometimes called disjoint events. So this particular term that we see here, when we have mutually exclusive, this term is zero, meaning that this cannot happen at the same time, so there is no intersection in between there. So let's take a look at a few smaller examples and let's try to illustrate this to you, and then I'll also talk about kind of that independent events and show you that mutually exclusive and independent event, they're not exactly the same thing. So let's imagine that all we're doing is, let's say, rolling a die. All right, so now our events that we're going to define, so if we're going to roll the die one time, okay, so that one time, okay, so let's say you can either roll a 1, you can roll a 2, you can roll a 3, you can roll a 4, you can roll a 5, or you can roll a 6. And let's say, just for the simplicity, that A, okay, would be defined, so this particular event is going to be defined if you roll a 1. All right, and now let's say B is going to be defined, okay, if you rolled, I don't know, a 6. So let's say you had something like that. Now the question is, if you roll the die one time, right? If you roll it, it is impossible for you to roll, and you're gonna have, you're gonna see a 1 and a 6 exactly at the same time. So those two events are mutually exclusive. You can't have a 1 and a 6 at the same time unless you possibly start rolling the die multiple times. Then of course, maybe on the first try you roll a 1, and then on the second one it might so happen that you might roll a 6. But if you're just rolling it once, it can't happen that both of them happen at that same time. So these two would be mutually exclusive, right? So you can either roll a 1 or you can roll a 6 right there, and then you can say that the probability of rolling a 1 is going to be just 1 over 6, and then the probability of B happening, right, is going to be also 1 in 6. That shouldn't surprise us because it's 1 in 6 for any number, okay, between 1 and 6 that we would roll. And now if we would do the probability of A or B, meaning what if someone says, I'm happy if I roll a 1 or a 6? So what that would mean is that you would have, okay, so that means probability of doing A or B is equal to the probability of A plus the probability of B plus the probability when they can happen at the same time. Now, we know that this is going to be 0 because if we're rolling it only once, then it's impossible for it to happen. So it turns out when you do have this disjoint, then the two events are mutually exclusive to each other. So within here, so the probability, we can just simply say is going to be 1 over 6 plus 1 over 6, which is going to be 2 over 6, okay, or simply just 1 over 3, in terms of trying to see if we're going to have a 1 or a 6 when we roll the die one time. So that would be mutually exclusive. Now, where else does mutually exclusive come about? Let's imagine that, I don't know, maybe you are playing baseball or something like that. And, you're a hitter, and then you're wondering what would happen to the hitter, okay, at a particular, at bat. So maybe the hitter is going to hit a single, or maybe they're going to hit a double or a triple, or let's say a home run, or maybe they'll just strike out or get some kind of an out. So the probabilities that you would have, you would have mutually exclusive events if you said that what's the probability of that at bat, so that batter, hitting a single, okay? Or maybe hitting a home run. Well, they can't hit a single and a home run at the same time. They would have certain probabilities associated with that single and that home run. And the happening of the two, they're completely disjoint. They just can't happen at the same time, right? So that's another mutually exclusive event. So now, how do these mutually exclusive events differ from independent events? All right, so let me try to illustrate. So let's take, for instance, the same die, but now also with the same die, okay, I'm going to flip a coin. And if you remember, rolling a die and then flipping a coin, those are two independent events. Just because you flip a coin, it's not going to have anything to do with you rolling a die. So if you roll a heads, okay, it's not going to impact, your rolling of die, and then depending on what you have, or what you're going to roll. So those are independent events. So I can say, so let's, I'm going to switch this up here. So let's say now I'll define A. It's not the same A. Okay, I'm redefining, so it will forget about the rolling of the die. But let's say, you're going to, my event number A is going to be flipping a coin and seeing a heads. And then, I'm going to have rolling a die and then, seeing a 1. So if I have something like this. Now, these two events are independent of each other. That's for sure. One will not have an impact on the other at all. But now, if you ask the question, if you flip a coin, and then you also roll a die, and then you say, well, what's the probability of seeing an A or B? So now the question is, if you're going to flip a coin and you're going to roll a die, can it happen that you actually will see both at the same time? Yes. You can flip a coin, see a heads, you can roll a die and you might see a 1. So they've happened at the same time. They might be two independent events, but they can occur at the same time. And in this case, if we were doing this right here, right, that probability of A intersected with B is no longer 0 because they can happen at the same time. And if they're not disjoint, that means they're non-mutually exclusive. So you have to be careful now of how do you calculate this. So how would we visualize something like this? Well, so I can rewrite what I did above. So let's say I'm flipping my die and then my coin. So I'm going to get a heads and a tail. And then I'm going to create a table here for myself just so that I can see that. So that is, with regards to event A would be just seeing a heads. And then as I roll, I can roll a 1, a 2, a 3, a 4, a 5, and a 6. And now, if I do them, simultaneously, so A and B trying to see, so sure, you'll notice here that I might get a heads and a 1, right? I might get a heads and a 2, a 3, a 4, a 5, a 6. So now all of these, if I were trying to find the probability of A or B, these work because I see a heads. Now, what if I flipped and I got a tail? Well, then the only one that would count is going to be the one that you would have seen a tail and a 1 because that's what I'm trying to see, A or B happening. If I see a tail or a 2, well, that won't work, okay? And none of these will work either. So now I can certainly count these up, right? Okay, because I can see them visually, and I'll see that, okay, well, it can happen 1, 2, 3, 4, 5, 6, 7, okay, and then there's 12 in total. So the probability of seeing an A or a B is going to be, just by simply counting this up, right, seeing the theoretical results, would have been 7 out of 12. But if you thought that these were mutually exclusive, then you would say, well, isn't it just probability of A plus the probability of B, okay? And then the mutually exclusive would have been 0, which is not the case, okay? But if you did this, you would have had and made a mistake. Because the probability of A would have been 1 over 2, right? So that's seeing a heads. Plus, okay, you have now the probability of B, which is going to be seeing a 1. So now seeing a 1 is just 1 out of 6 on the die. And if you would do this, right, so if we, let's say, span it over 12 in terms of a common denominator, so this is going to be 8 over 12, which clearly is too much, okay, than what it should be. And that shouldn't surprise us because of the fact that we had this heads and a 1 happening simultaneously. So if we really wanted to know what the answer is, sure, we can do this plus this, but then, okay, this is not going to be 0. This is going to be, we have to take away the probability of when A and B happen at the same time. Now, it only happens once, right? 1 out of 12 times. So that would have been 8 over 12 minus the 1 over 12, and that brings us back to 7 over 12. So within here, these two events were independent. But if you do them at the same time, they may yield you a result that is not necessarily mutually exclusive. So be careful with that, right? Okay, so mutually exclusive means that if you're going to be performing two events, that they can never happen, okay, at the same time. That would be mutually exclusive. So that A intersected with B, or if you have many more events, okay, is completely disjoint between them. So that is something that you're going to have to think about. And I was trying to give you here the couple of examples where this might come into play. And then you can also think about baseball or any other things that might happen, right? It's kind of like even thinking about, we might think that we're multitaskers, right? Where we can do multiple things at the same time. But the reality of it is we can't, right? We can disjoint the tasks and then intertwine them so it feels like we're being, okay, or we're doing something, okay, and we're multitasking. But at the end of the day, right, I can only speak at the moment, right, as I'm talking to you throughout and then completing this particular video. You know, I can't do this simultaneously, you know, let's say with maybe going to the washroom. I would have to stop this, okay, go there, okay, and then come back. So I might still feel like I'm multitasking, okay, but the reality is that those two events were disjoint, okay, altogether. All right. Now, okay, it is tricky, okay, figuring and learning about mutually exclusive, and then also not confusing it with independent events. Independent events, remember, means that if one event happens, it has no impact on the other event. There's no dependence, okay, at all between them, okay? That is different than being mutually exclusive, which means can they happen at the same time, right? Throwing a heads and seeing a 1 can happen at the same time, but the two events are independent, all right? Okay, so thank you for watching, and I hope that you found this video a little bit useful, okay? And we'll see you in a future one. Bye, everybody.